For this experiment, we will need a test tube, water, a candle, a boiling stone, matches, a test tube clamp, and a rubber stopper. A boiling stone is placed in the test tube to help reduce the chances of the water bumping when heat is applied. Water was added to the test tube. A test tube clamp was used to safely hold the test tube over the flame. Watch carefully as heating begins. Record any observations. Look carefully at the inside of the test tube. Focus your attention on the wall of the tube just above the boiling stone. You should see bubbles. Are they large or are they small? Are they moving or are they stationary? What do you think the bubbles are? A new set of bubbles is ready to emerge. The rubber stopper was placed into the test tube. Was it placed firmly or loosely? Are the new bubbles large or small? Are the new bubbles stationary or in motion? What are these bubbles composed of? What is forming on the inside of the glass? What is escaping around the rubber stopper? When heat was first applied to the water, the temperature began to rise. Above the surface of the water, there are molecules escaping into the gas phase. Those molecules exert pressure on the inside of the container. As the temperature of the water rose, more molecules escaped into the vapor phase, and the pressure exerted by those molecules increased. At 100 degrees Celsius, the vapor pressure finally reached the atmospheric pressure and the water began to boil. As boiling continued, more and more fast-moving water molecules entered the vapor phase. The water molecules occupy space. They collide with air molecules and push them out of the test tube. As time goes on, more and more of the space inside the test tube is taken up by water molecules in the gas phase. Eventually, there would be no air left. Notice the stopper is being pressed tightly into the test tube, and that boiling, well, what happened to the boil? The heat was removed and boiling stopped, and yet we see little bits of boiling occurring as it cools, even though the heat source has been removed. Now the test tube is inverted. The only new heat being supplied is coming from the experimenter's hand. How is it that the water boiled so far below its boiling point? It's time to record the answers to our questions. Question 1. When heating first began, small bubbles formed. Were the bubbles moving or were they stationary? A. The small bubbles were moving. B. The small bubbles were stationary. Question 2. What do you think the bubbles were formed by? A. Water vapor. B. The release of dissolved air. Question 3. Once boiling started, a rubber stopper was placed on the test tube. Was it placed firmly or loosely? A. Firmly. B. Loosely. Question 4. A second set of bubbles appeared. Were the new bubbles large or small? A. Large. B. Small. Question 5. Were the new bubbles stationary or in motion? A. Stationary. B. In motion. Question 6. What are these bubbles composed of? A. Water vapor. B. Dissolved air. Question 7. After boiling commenced, something happened to the walls of the test tube above the boiling liquid. What was forming on the inside of the glass? A. Water vapor condensed back to liquid on the cool surface of the glass. B. Water rose up the walls of the test tube by capillary action. Question 8. As boiling continued, what was escaping around the rubber stopper? A. Air. B. Water vapor. C. Both of these. Question 9. Eventually, heat was removed and the rubber stopper was A. Removed from the test tube. B. Pushed firmly into the test tube. C. Placed loosely on the test tube. Question 10. As the test tube cooled, some of the water vapor A. Boiled out of the test tube.
B. Poured out of the test tube. C. Condensed back into the liquid state. Question 11. At this point, the pressure in the test tube, blank, and the boiling point of the water, blank. A. Increased and increased. B. Decreased and increased. C. Increased and decreased. D. Decreased and decreased. Before we finish, let's take a moment to review the boiling process that we observed. There will be one more question at the end, so stick with it. We all know that water evaporates. That tells us that in an open container, water molecules are continuously escaping from the liquid phase into the vapor phase. As the water is heated, the molecules in the water absorb the heat and begin to move faster. They begin to exert more force on each other as they collide. As the temperature rises, more and more of the molecules have the energy they need to break free from the liquid state and to escape into the vapor phase. Molecules in the vapor phase are moving too. At a given temperature, vapor molecules have more energy than liquid molecules. They collide with each other, they collide with the walls of the container, and they collide with the other molecules of air they share the container with. Through these collisions, the water vapor molecules exert pressure on the system they are in. The pressure exerted by the vapor is called the vapor pressure. As the temperature rises and more molecules escape into the vapor phase, the rate and intensity of the collisions increases. In other words, as the temperature of the liquid rises, the vapor pressure of the water rises. Above the water, there's a stack of air molecules moving all the way up through the sky. The earth is pulling down on them, but they are moving and colliding just as the water vapor molecules are. The weight of those molecules exerts pressure too. As the temperature of the water continues to rise, the vapor pressure continues to rise. Eventually, the pressure exerted by the water vapor is just as strong as the pressure exerted by the stack of air molecules. At that point, it becomes very easy for the vapor molecules to push their way through. And as they do, so long as heat is provided, more liquid water molecules will escape into the vapor phase. The water boils. As it turns out, the boiling point of a liquid is the temperature at which its vapor pressure equals the applied pressure. For water at 1 atmosphere of pressure, that temperature is 100 degrees Celsius. If the applied pressure was higher, the boiling point would go up. It would take a higher vapor pressure to freely push the molecules past the air. At first, the vapor molecules don't get far. There are plenty of air molecules in the test tube, and the surface of the test tube away from the flame is relatively cool. Heat flows from high to low. High energy water vapor striking low energy glass will give energy up to the glass. Give up enough energy and the molecules will fall back into the liquid state. We see this as condensation occurring on the walls of the test tube. As boiling continues, the escaping vapor molecules push the air molecules out of the test tube. In time, only hot water molecules fill the space above the liquid. The air is gone. When the stopper was pushed into the test tube, forming a tight seal, air was prevented from re-entering the test tube. As the water vapor cooled, much of it condensed back into the liquid phase, leaving a smaller number of molecules in the gas phase than were present when the distillation began. The pressure inside the test tube was lower. At lower pressure, the boiling point of the water is lower. All that was required to heat the water to boiling was the warmth of the experimenter's hand. The boiling point of a liquid drops as the pressure applied to the liquid drops. The boiling point of a liquid increases as the pressure applied to the liquid increases. Question 12. Thank you for your participation. Would you like to receive 7 points just for participating? A. No thanks, I've done enough already. B. No thanks, I don't really need them. C. No thanks, points are really overrated. D. Yes, I'll take those points. E. No thanks, I don't want to be greedy. This concludes today's laboratory assignment.